All right, let's talk about section 9.5, graphing trigonometric functions. All right, so to kind of give you a short version of the story, we can take what we learned in the unit circle in the last section, and we can turn that information into curves on the xy axis. If we take theta and we plot it on the x-axis, and then we take whatever the values of sine are and plot those against the y-axis, then at 90 degrees, for instance, sine is 1 in the unit circle. At 180 degrees, sine is 0, and so on. You can keep plotting all of these points, and you get this sort of curvy, squiggly graph here called the sinusoidal curve, and that curve is going to be very similar to cosine, except you'll notice that cosine starts at a different spot. So a few things about these graphs, and we'll look at them in your calculator here in a second. But a few things about them. The domain is all real numbers for both. They go forever to the left and to the right. Okay. The range in the basic curves just go from -1 to 1. That's the y values covered by the graph. The amplitude of each is 1. Now, amplitude is a new word, I believe, that we haven't talked about yet. The amplitude of a curve is the distance from the midline to the top. Okay, so this here is 1. That's the amplitude. That's A. Okay, from the midline to the top. Okay, and so if you think about like a wave, like in the ocean, if we say it's a 3-foot high wave, then that's what's being measured, is the distance from the middle of the midline of the wave to the top of it. All right, the period, the distance it takes to complete one cycle, is 360 degrees. You can see this curve is going to go up, back down, and come back to that starting spot every 360. Same thing here, except that this one starts at a maximum, or at the top. That distance right there is still 360. Okay, this is for the basic sine and basic cosine, where we have not added any numbers in here. Okay, so what else do I want to emphasize here? All right, well, a few things. So y, the basic sine curve is y equals a sine. This is a times sine of b theta. Okay, and the basic cosine curve is y equals a times cosine of b theta. And this is important because it helps you figure out because with this information you can figure out the amplitude and the period. So amplitude is, this is all written over here, but it's not, it's written pretty small, and you really need to have this at like easy access. So amplitude is going to be equal to the absolute value of whatever A is. And the period is going to be always equal to 360 over B. The book uses the absolute value of B. Technically that's true. Just remember that you only need the positive B value, okay? This will give you the period. Remember, that's the distance to complete one cycle. Okay, so that's all really important information. Let's do an example here where we're trying to find the amplitude and the period of y equals 4 cosine 3 theta. Okay, so we're going to get a graph of it as well. But we can actually answer the question of amplitude and period without the graph. Okay, this is our A value, and that tells us the amplitude or the height of the graph. So our amplitude is equal to 4. The period, we can get that from the B value, right? Here's B. Period is equal to 360 over B, so I'll take 360 over 3, and that'll give me 120 degrees. Okay, so the period will be 120. Now, I want to show you how to do this in your calculator. If you are using a TI 84, 83, TI, whatever, you want to first take a second to set your window, max and min, to whatever you've got in the graph. But here, as a good rule of thumb that you can kind of set it to, and usually you will get enough of the graph that you need, is -90 to 720 is a good rule of thumb for the x's, because remember, we're thinking in terms of degrees along the x-axis. And then for the y's, -10 to 10 is usually a little bit too high. Depends on what the curve is, so you can always sort of tweak that if you want. I'm going to switch it to -5 to 5 to match the curve or the graph that's given here. And in Desmos, you can do sort of a similar thing, but that's what you want your window setting is, or at here. And then in your calculator, you're going to go 4 times cosine, cosine of, in parentheses, 3, come on, 3, and then instead of using theta, you can just use x, okay? So you can notice there is actually a theta on the button, but you can just use x. And then hit graph, and you can kind of see what kind of graph is generated here. Okay. The other thing that you can do with your graphing calculator is set your table. So it starts at 0, and this is the change in table. Usually it goes by 1s. You can set this to go by whatever you want. I look at this graph here, and it goes by 45, so I'm actually going to set it to 45. And then when I go to my table, I can see that it gives me points on intervals of 45. And I can just plot those points. So I'm going to plot 0, 4, that's where it starts. And I can go backwards too, right? So I can go to negative 45 at negative 2.8. So that's about right here. And 4, 2.8, no, I'm sorry, 45, negative 2.8. Whoops, that would be negative, sorry. Okay, so 45 is at negative 2.8. At 90, it's at negative, oh, sorry, at 90, it's at 0. At 135, it's at positive 2.8. At 180, it's at negative 4. And so you can kind of see what's going on here. The thing is going to go down quickly, back up, and it's going to have to come to 4. You can see that in the graph. So like if you hit trace, oops, you can see that it tops out there at about 4, about 240 degrees. Okay, and then it comes back down. And back up. Sorry, this is not a beautiful graph here, but it's just going to keep doing that, okay? And then you're going to come back the other way and keep going. Okay, so most of the graphs are not going to be squeezed like this. This was actually a bad example probably to put in the notes. All right, maybe we'll keep going. You get the idea though. You're going to be plotting points and sketching the curve through it. There's nothing new there, so this will just kind of keep going on here. Ignore the fact that I'm off a little bit, just to save us some time in the video. But that's the idea. In Desmos, the first thing that you have to do is make sure that you're in degree mode. So you hit the little gear. You're going to flip it to degrees. You're going to put in your curve. And so it would be 4 cosine of 3 times x. Okay, and you can see here, I can't see much of the curve. But if I go change my x min and max, so maybe I make this negative 90 like I did before, and then here I'm going to make this 720, that, and then I get the curve, okay? And then you can either trace with your finger or the cursor to get the points. You can see where the intercepts are here. I probably should have just done that. But anyway, you can see the intercepts there, you can see the maximums there, and as with most things, it's nicer in Desmos than the graphing calculator. Okay, so we already did all of this. So I don't think we need to do this. The amplitude is the number in front, and the period can be found with the b value, or I guess I should say with the formula or the graph. You could have also figured it out from the graph. All right, let's shift gears to talk about tangent here for a little bit. So tangent is much different because tangent is actually, you don't need to know this for the test or anything, but it's actually sine of theta over cosine of theta. That's how you get tangent. And because sometimes cosine of theta is 0, sometimes you'll get vertical asymptotes. Okay, so that's why this graph looks so strange, is you have these vertical asymptotes at intervals of every 180 degrees, you get a vertical asymptote. So that's why this curve looks the way that it does. The graph of tangent in the form a tan of b theta, the period is 180 over b. There's no amplitude, okay? So that's going to be a question on the quiz usually, and the students will get that wrong sometimes. There's no amplitude. That's because it's not a wave. Amplitude only applies to curves that are waves. The asymptotes are always at odd multiples of 180 over 2b, okay? So a couple notes over here. Asymptotes will show up as vertical lines in your calculator if you're using a TI-83 plus. Okay, if you're using one of these, the 84s, or the 84 colors, then you'll be fine, because, so like if we just put tangent in here and graph it, you'll get smooth curves. It doesn't draw in the asymptotes, okay, so then you're fine. But if it's an 83 plus, like one of the red ones from the school, you're going to get vertical lines in there, and you have to remember that they're not part of the graph. This year, if you use Desmos, then Desmos will not put those vertical lines in there, and you will just get the smooth curve like that. Okay, there's no amplitude, and make sure that you follow the formula to get the period. That's the basics of graphing a tangent curve. Okay? All right, so let's do just one example of tangent here. Tangent of 2 theta. Okay, so again, I'm going by intervals of 45, and I want to put in 2x here. And of course, again, this is going to be really squished. Let's go and actually use Desmos, so I know I'm cheating a little bit here. Maybe that's not really cheating, I guess. So let's put tangent of x in here. Okay, and so you can see that we've got intercepts at every 180 degrees. So at 0, 0, 180, 360, okay, there's where our intercepts are, and then you can see that there's going to be vertical asymptotes here, and you're going to have to sort of figure out where that is. But one thing that you can do is you can trace the graph, and you can see that, like, as you go down, you can see what the x values get closer to. So it's hard for you to see probably, but it's getting closer to 90. Okay, so here at 90, you're going to have an asymptote. Here at negative 90, you'll have an asymptote, and that's where you just kind of sketch these cubic curve-looking things in between your asymptotes. In the graphing calculator, like if you go to the table, they'll show up as, you could do the table in Desmos as well, but if you go to the table, you'll see they show up as errors. And I put them in the wrong spot. I'm sorry. They're at negative 45 and 45. I should have looked closer at Desmos. So they're at negative 45 and 45. Oh, that's because I didn't put 2x in there. Sorry. Here's what the curve looks like in Desmos. Okay, again, I picked one that was 2. The period was too short. We'll just get one of these cycles right here. Sorry guys, this is not my best video ever. Okay, so here we go. Okay, and then we'll have another one. At 135. And that cycle will just keep repeating over and over. Okay, let's find the period here. The period is going to be equal to 2 pi, or I'm sorry, pi over 180, or 180 over pi. Gosh, it keeps getting worse. 180 over b, I'm sorry. Period is equal to 180 over b. B in this case is 2. Okay, so 180 over 2, so our period is 90. We could have gotten that from the curve as well, because the distance from here to here is 90 degrees. All right, and then we want to figure out the formula to find the asymptote. So where they land, if we had done this first, I wouldn't have messed it up. But anyway, it's 180 over 2b. So that's 180 over, in our case, it's 180 over 2 times 2, so 4. So that's going to be at every 45 degrees. Yeah, I think it's plus or minus. And that's what we got here. Plus or minus 45 degrees were the asymptotes. And then they just keep repeating. So once you find that it's at plus or minus 45, then it will just keep repeating whatever the period is. So one will be at negative 45, for example, then at positive 45, then at 135, and it will just repeat every 90 degrees. All right. Last thing, secant, cosecant, and cotangent graphs, you just graph 1 over the main function. So cosecant 1 over sine. Y equals secant of x is 1 over cosine. And y equals tangent of x. Sorry, y equals cotangent of x is equal to 1 over tangent. Okay, so if you have to graph any of those, that's what you do. Those are sort of fun graphs because they look pretty different than just sine and cosine. But that pretty much wraps it up for section 5 here.